Hello, my name is Andrew, and today we will be going over problem 14.18 in Introduction to Chemical Engineering Thermodynamics by J.M. Smith. So a quick overview of the problem. You see it here in the middle of the screen. The production of 1,3-butadiene can be carried out by the dehydrogenation of 1-butene in this reaction. Side reactions are suppressed by the introduction of steam if equilibrium is attained at 950 K and 1 bar, and if the reactor product contains 10 mole percent 1,3-butadiene. Find A, the mole fraction of other species in the product gas, and B, the mole fraction of steam required in the feed. So we start off here with our reaction. We have 1 mole of reactants and then 1 mole of each of the products. And our reaction carries out the dehydrogenation of 1-butene, gives 1,3-butadiene. We start by finding V, the stoichiometric number. We have reactants being consumed with the -1, and then 1 mole of 1,3-butadiene and 1 mole of hydrogen gas right here. And then I just state the conditions of the reaction. Side reactions are suppressed by the steam. Equilibrium is attained at 950 K and 1 bar. So now we start by finding the mole fraction. We are starting with a 1 mole basis and a 1 plus X mole basis of steam. We start off with our equation. NiO equals 1, V equals -1, NO equals 1 plus X. After plugging them in, you can find what your equation would be for the mole fraction of species 1, and then species 2 is the supplement to the reactants, so species 2 and 3 are as follows. And from stated in the problem, the mole fraction of reactor products is 10%, so we know these values. So here's where a lot of work for the problem comes in. We need to find delta G, and we can find delta G by using our ICPH and ICPS functions for estimating entropy and enthalpy of reaction. And then for this part, you need to consult table C4, which is located on page 658 in the e-textbook, to find H0, delta H0 and delta G0. So really quick, I have table C4 pulled up. Standard enthalpies and Gibbs energies of formation at 298.15 K. We can see that 1-butene is located, over here. And then we have 1,3-butadiene located here. And then you see for the next part, we need to find delta A, delta B, delta C, delta D. And we can see here below that I have the names of the species listed with all the values of A, B, C, and D, which are found in table C1 in the textbook. Pulling up table C1 really quick, we have the heat capacities of gases in the ideal state. We have butene right here, 1,3-butadiene right here, and hydrogen right here. Substituting all of those values, we find delta A to be 4.016, delta B to be -0.00422, delta C to be 9.01 times 10 to the negative 7th, and delta D to be 8,300. After substituting all of those into this equation, we find that delta G equals 4,896 joules per mole. Next, we use K, plug in delta G, R, and T. We find K to be 0.5197. Now we have to find epsilon, so we plug in our values from above. Right over here we substitute, and we get epsilon to be equal to 0.8386. Next we will find X, plug in our values that we have found above, 0.8386 for epsilon. When you solve for X, you get X equal to 6.5474, and now we can find our mole fractions of the species and steam. So here we plug in our values for Y1. We get Y1 equal to 0.01946. Scroll down, we see here we have our calculation for mole fraction of water, which turns out to be 0.78054. Lastly, we have our steam calculation, which turns out to be 0.8675 mole fraction of steam required in the feed.